Okay, so hello and welcome everyone. This is the Ethereum Engineering Group Meetup, and today we've got Piper from Ethereum Foundation, who's going to talk about the Ethereum and you've changed the title, haven't you? I was going to say decomposing the monolith, etc., but it's not. It's democratizing Ethereum. So, before you share your slides, could you introduce yourself, please?
Certainly. Let's see. I've been around for a while, not as long as some, but I was in this really nice spot the day that the network launched, where the company that I worked for and I had decided that we didn't really like each other that much. And they gave me the last month to find a new job. And I spent that finding a new job and figuring out how Ethereum worked. And that was when Frontier launched, and I've been kind of doing that ever since. I run a team at the Ethereum Foundation, mostly a bunch of Python people. It's been getting a little bit more diverse in terms of what we do in the last year or two. And we focus a lot on ecosystem development, building tools for people to use, building tools for us to use for research, and focusing on the actual core protocols that run the whole thing. Looking at them, staring at them, ripping our hair out, trying to figure out how to fix the things while the engine still churns on without breaking everything.
Thank you. All right. And one other question before you start. So when did you say you wanted to have questions? Was it?
I have some pauses or some specific just slides that say pause for questions. So if you have a question, I would love to answer it. There will be 2 or 3 spots in the presentation in which there will be good times to ask those.
Okay, that's brilliant. All right, well, thank you. So please share your slides and let's hear all about decomposing the monolith, democratizing Ethereum.
There you go. All righty. Can we see that?
Yes.
Excellent. Cool. Well, I already said it, but I've been rehearsing this all day, and it starts with, my name's Piper Merriam, and I work for the Ethereum Foundation. Today, I am here to talk to you about this idea, democratizing Ethereum. I just sort of stumbled across this, and I liked the word, and so it's what I used. I think that we have a problem. The problem is that it is difficult to access our protocol. But first, a little bit of a roadmap here. So this is what we're going to do here. I'll go over kind of defining what the problem is. We're going to talk about light clients and what I mean by light clients. And I'm specifically talking about defining them well, because I do not mean the same thing that exists today as a light client. We're going to talk about what we actually need to build functional light clients. And then we're going to talk about that solution of how we actually build those things so that we can have the light client that I want us to have. Here's a graph I made up. On the upper right-hand corner here, we've got the logos for all of the kind of like major Ethereum clients. Ethereum clients are heavy. We've got kind of these 2 axes here, light and heavy. We could call that like easy and difficult, and centralized and decentralized. Running a client is a great way to interact with the protocol. It gives you access, straight through your client through things like the Json Rpc interface to interact with the chain, look up blocks, send transactions, all of that stuff. But the cost is high. It is expensive to run a client in terms of running it in the cloud is actually financially expensive, but just running it on your machine is likely to cost you 1/4 to 1/2 of your disk space and a lot of CPU if you want to keep it running. On the far corner of this graph, I've got the Infura logo. This is meant to just sort of symbolize centralized providers. So we've got these 2 extremes. Centralized providers are really easy to use. You don't have to run any infrastructure at all. You grab yourself an API key, or maybe you can even use them on some sort of free tier. And we pay with the cost of accepting central points of failure, privacy implications, things like that. These things exist at kind of the far end of 2 ends of a spectrum of really core, like leaning into the decentralized ethos and running your own infrastructure to just giving everything up the way that we gave up the rest of the internet. And we kind of saw where that went with, well, what the internet looks like today. What I want to talk about today is the missing piece in, I never know if Zoom mirrors these things sometimes. It's in the upper left corner for me. It's where the question marks are. This is the place that there is no good solution, and there should be, because we should have a way to talk to the protocol that doesn't require us to sacrifice privacy, lean on central points of failure, and that also doesn't require us to have a big beefy machine running a big beefy piece of software. I mean, my laptop turns into a space heater when I have a client running. They are computationally expensive. An astute reader may say, what about LES? LES is the Light Ethereum subprotocol. It's been around for about 4 years. It's when people say light client in the Ethereum context, this tends to be what they mean. LES has never delivered on the promise of reliable light infrastructure. LES has what I consider to be a fundamental flaw in its architecture, which is the server-client model. Not all nodes on the LES network are the same. You have servers and you have clients. The servers provide all of the data, and the clients request that data. There's no clean way or easy way. There's really no way for the clients to really give back to that network. So they are purely a consumer, and the servers are the service providers. And if there is an imbalance there, if there are not enough servers to meet the needs of the number of clients on that network, then the experience as a client gets worse and worse until eventually you can't get any data at all. This has been my experience with this network. Without dedicated servers that are there for your client to connect to, using LES tends to be unreliable. It's difficult to find servers to connect to, and even when you do, they tend to be somewhat overloaded. One of the proposed solutions for this is incentives, but I don't really think that this actually solves anything. It does allow us to solve some little thin slice of the use case for whoever it is that is willing to pay for this data, but I think that the internet has shown us pretty clearly that people aren't that inclined to pay for stuff. I just don't believe that incentives actually solve this at the scale that I'm interested in solving it. I think LES has a place in our ecosystem, but it is not going to deliver the light clients that we want. That's my opinion. So when I go back to this graph, we can shove some use cases or whatever you want to call these into this corner of what we're talking about. And the reason that I want to look at this is that I think that this is a massive market that is not being served. I think that just some numbers to pull out of thin air. There's about 10,000 nodes on the Ethereum network, and there's something like 1 million people who have installed MetaMask. I might be making that number up, but there's definitely more people who use MetaMask than run a full Ethereum node. Wallets have a very light footprint in terms of how they consume the protocol. Casual users or new users who are tinkering around with the protocol, same sort of thing. They're not consuming tons of data. They're poking it and writing their first ERC20 contract and checking their balance and whatever that is. And at the risk of getting into kind of buzzword territory, resource-constrained devices or low-resource devices. There's always been a lot of talk about Internet of Things and blockchain. But the reality is that if you want to take an Internet of Things device, a Nest thermostat or whatever, and have it talk to the Ethereum protocol, you're going to have to step through some intermediary, which is either running an Ethereum node yourself, which is heavy, or using a centralized provider. There's no there's no option for that device, that low, small, resource-constrained device to interact with the protocol itself. And we should fix that. I think this is a huge market. I didn't even try to quantify it, but there is a huge pile of use cases sitting in here that have no solution other than to use something like Infura or to lean on their own central infrastructure. And it would be great if they could just talk to the protocol themselves. So for the rest of this talk, when I say light client, I do not mean a client on the LES network. I mean something new and something that doesn't exist today and something that you can't build today. But it is something that we can build. So we're going to define what we mean by light. I mean that it can run on a resource-constrained device. I mean that it does not have that the UX for using the client does not involve syncing. You turn it on and you use it. There's no waiting. There's no sitting around waiting for it to catch back up to the chain. It's there and ready to use when you want it. We want to build these things out on top of a network that truly scales to arbitrarily large sizes. Like I said, there's 10,000 full nodes on the Ethereum network today. It's totally non-trivial to bring on 1 million of these things if it was out there and existed, because we have lots of more people using wallets and other things like that. And the core piece here is that it absolutely must expose the Json Rpc API as an external interface. This is a very standardized API that most software that interacts with Ethereum uses as its gateway to talk to the chain. This is what Infura exposes. This is what the Json Rpc server in any of the clients expose, and it's what this new type of light client needs to expose. So when I say resource-constrained device, I mean things like Raspberry Pis, mobile phones, or just your regular old developer laptop, but something that's so lightweight that you can leave it on as a daemon process in the background, never turn it off, and never really be affected by the overhead of running it all of the time. Yep. So we also have to eliminate syncing. The UX today, when you want to use one of the Ethereum clients, is install it and now wait 6, 8, 12 hours, 24 hours for it to finish syncing, after which you can start interacting with the network. We get similar things if you've been offline for like a couple of days. I run my Geth node every once in a while, but when I find that I want to use it to send a transaction, I often realize that I'm gonna have to wait a couple of hours for it to catch back up with the chain. My team in the last couple of years built out this prototype called Beamsync in our client that we wrote called Trinity. And Beamsync was essentially a proof of concept to show that it is absolutely possible to build mainnet clients that do not suffer from this UX barrier. And I'm not going to get into the details of how that works, but the important part is here is that we've shown that this can be done. So I'm losing the thread. So we need clients that don't suffer from this like really horrible UX of having to wait hours before you can use them. We need a network that scales arbitrarily large. We have clean examples of networks that do this. BitTorrent does this. The core protocol that Ethereum clients use does this well. And really this is sort of stabbing at the client-server architecture of LES, because we don't want to replicate that. We want something that isn't about making sure that there's enough servers online to deal with all the clients and having growth issues when new people join and needing to somehow figure out how to get more servers on. We need something that's just going to work whether or not you throw 10,000 nodes at it or 1 million nodes. And the Json Rpc API. This is just a hard requirement. It's how you interact with the protocol. And a client that doesn't expose this doesn't actually give you very much to work with. So backing up here real quick, low resource devices is just being able to operate on those is just a function of paying careful, close attention as we design whatever protocols this light client lives on top of. We have done the work to show that we can make a client that doesn't suffer from the UX horribleness of waiting for clients to sync. And we have existing networks that show us that we can build things that scale if we pay close attention and design them that way. So most of the rest of this talk is going to be focused on how what we need in order to expose the Json Rpc API and sort of how we get at that underlying data that's necessary for that. But first, this is a good point to pause for questions. Who's got one? Now I've waited just an awkwardly enough amount of time.
Yeah, I think Piper, everyone's fully understood everything you've said, so it's
Cool.
all good.
I'll call that perfect.
Yeah.
All right. Moving on. So Json Rpc API and the underlying data that we need to serve this. This is not a list of all of the Json Rpc endpoints, but this is a representative list of all of the Json Rpc endpoints that involve needing data from the Ethereum network. One of the nice things is that when we look closely at what's needed to serve these, they divide themselves up very cleanly into these three categories. We've got gossip, which is essentially just tracking the head of the chain. This is how transactions make their way around the network and find their way into blocks. This is also how clients find out about new blocks. We have state operations, things like checking your balance or things like reading contract data, estimating gas for transactions. These interact with the state, and when I say the state, I mean the collection of all of the account balances and all of the contract storage and all of that stuff. And we have history. This is just all of the 11 million plus headers that go back to Genesis, as well as the block bodies that go with those, as well as all of the receipts and things like that. Okay. This is the data that you need in order to expose the Json Rpc API. So the thing that I'm trying to point at here is that if you have access to this data in the right format, you can build these endpoints on top of it. And so for us to have functional light clients, we need the ability to get at this data in the right ways. And we need the networks that these clients are part of to be lightweight enough so that they can run on resource-constrained devices, things like that. But if the data is there, we can build the clients that interact with it. That has been one of the key pieces that's missing today, and why we don't have a way to access the protocol in a lightweight way, is because there's no way to get at the data in the manner that we need. Here's one example of one of the things that makes it hard to write a lightweight client today. We've got these three Json Rpc endpoints, looking up a transaction by its hash, getting a block by its number, looking up a transaction receipt by the transaction hash. Ethereum's got this mechanism called uncle blocks, which are blocks that were mined at a given height, but that didn't end up being the canonical block in the chain. And so they end up getting included in a block higher up somewhere as an uncle. When the Ethereum client syncs the entire history, what they do is they build up this mapping, this index of block number mapping to block hash as they figure out which blocks are canonical. The same thing goes for transactions. Transactions can actually be in multiple blocks, but only one canonical block. There may be an uncle on which the transaction is mined, but that's not the canonical block. And so what we need is a mapping of transaction hashes to block hashes. Any of you who have an Ethereum node on your computer have 500 megs of block number mapping to block hash, and you guys have 32 gigabytes of transaction hash mapping to block hash. There's basically 1 billion transactions that have happened, and that is a very big number, and even that small little mapping adds up to 32 gigabytes of data. This is the type of thing that the current core protocol does not do for you, because clients do it for themselves. They download all of the chain history, they build this index, and that is the only way that they can serve you transactions by their hash or blocks by their number. If we're going to have functional light clients that can serve the Json Rpc API, we have to move this functionality into the network itself. It has to be part of the water. It's got to be built in, because it is too high of a burden to put on the light clients. This is an example of the type of thing that has to be fixed. And we can kind of just look at what it's like to serve Json Rpc requests from the full node and light node context. It's hard for me not to just read this slide, but full nodes hold all the data, they do the heavy lifting themselves, and they serve the Json Rpc request from the data that they're holding on to. And we have to completely change this so that light nodes, there's no presumption of local data. There's no presumption of being able to do some of these expensive things locally that the network isn't doing. And all of the Json Rpc requests have to be servable on demand from data fetched from the network when the request comes in. So let's get down one level further and talk about the data that we need and the protocols that we need to build this, because this is how we get to a place where we can have functional light clients. So today, in the network that exists today, all Ethereum nodes exist on the ETH protocol in the Dev P2P network. This is a peer-to-peer network. It's got this concept of sub-protocols. ETH is one of them. LES is another. There's a bunch of other ones out there that random people have made. But the core protocol is the ETH Dev P2P protocol. It contains all of the data that we need to build a light client, but it does not expose it in a way that is conducive to building light clients. It has all of the gossip information. It has all of this stuff for accessing the state. It has all this stuff for accessing the history, but all of these things are really tuned towards the role that clients play today, which is syncing all of the data and holding onto all of it and serving it locally. This network has served us well. It has been stable and reliable for years, and it has been the backbone of our chain. And we've tried to do things like building something light on top of it. And the conclusion that we've come to is that it is just not suited for this because it does not expose the data in the way that we need it. This is what I call the monolith. I think of the ETH protocol as this kind of monolithic thing. The data divides itself up into these nice kind of three different categories. And they really are three nice independent categories. The history is basically one big append-only file. The state is like one big piece of RAM that's randomly being accessed all of the time and changed and modified. And gossip isn't data, it's just the information channel through which the data comes to you. But the ETH protocol rolls all of these and bundles them into one, and for good reason. It's much simpler to do that way. Some other nuances that are part of why the ETH protocol is not conducive to building a light client on top of it is that it has this implicit requirement that all nodes in the network store all of the state and all of the history. There is no mechanism that allows for nodes to forget things like old blocks or old history. And if you try to be part of this network without having the full set of data that is that the network wants you to have, and that the requests that other clients send you expect you to have, then you're not going to be able to maintain consistent peer connections, because peers will mark you as useless because you can't respond to their requests and they will disconnect from you. So it's not possible to be part of this network and do these things in lightweight ways. We need something different. And this is where the deconstructing the monolith comes in. My intention is to take this network apart and build 3 new networks that serve these roles well. That doesn't say that we're going to get rid of the ETH protocol. The ETH protocol does what it does, and it does it well. And to try to get the ETH protocol to do both of these things well is the wrong approach. We've looked at that, and it's tempting, but it doesn't necessarily work. And one of the main reasons that it's the wrong approach is that the ETH protocol needs to be stable. It is expensive to make significant changes to it because it means all of the clients have to make them, And it means that we have to be super careful about those changes because we cannot break it. It is the core of the network. And that's why I'm looking at this through this different lens of how do we build out special purpose networks that can serve the data that we need in the manner that we need it. And the nice part is that if we build these out separate, we are sort of free from the extremely high burden of correctness that the core central backbone of the protocol requires. These networks can be a little bit unreliable. They don't have to be totally bulletproof. They just have to work almost all of the time, whereas the ETH protocol needs to work all of the time. So we're going to dig now down into kind of each of these individual pieces, and I'll talk about what it looks like to build these things out. These are active topics of research. None of these exist today, but they are what myself and my team and some of the other researchers are going to be focusing on over the next months and year and whatever to build these things out, because without them, we can't get to a spot where we have lightweight clients. It's just not likely to happen. We'll talk a little bit about how this plays into stateless Ethereum towards the end, but I don't want to veer off too far in that direction right now. So the gossip network is one of the first things that just sort of like everybody needs. Clients that are syncing need it, clients that are fully synced need it, and a light client needs it. We need the ability to follow the tip of the chain, and we need the ability to, as a light client, inject transactions into the pending pool of all transactions. One of the more complicated pieces that maybe it's not more complicated, one of the complexities that shows up as we try to solve this problem is dealing with the transaction pool. Being able to be part of transaction gossip as it exists today in the ETH protocol involves validating transactions, which involves access to the state. Because one of the validity checks that you have to perform on a transaction is, does the sender have enough money to pay for this thing? And if you don't have access to the state, then you cannot validate a transaction. And that is one of the requirements that clients have to fulfill, because otherwise somebody can spam the network with large numbers of transactions that can't pay for themselves, and this is a large DOS vector. So this validation step is very important for DOS mitigation. So as we build this network out, it is likely that what we're going to be looking at doing is bridging it with the core Ethereum protocol, and essentially figuring out ways to throw transactions over the wall into the core Ethereum protocol, while placing as small a burden as possible on the members of this network to continually relay them among themselves, and which implicitly requires validation. By the way, the gossip network is probably one of the easier ones to do. It's likely that we build this out over something like dev P2P. Gossip networks work well in that protocol. We might use libp2p if that seems to be the right thing. But the core piece here is that the Ethereum protocol exists on TCP and on long-lived connections between peers. And while this doesn't work super well for the other protocols I'm about to talk about, for gossip, it actually works absolutely well enough. And so in terms of actual technology choices for building this out, it's very likely that it may just be another dev P2P protocol or something on libp2p if that is where things are going at the time that we build this. The other network that we need is history. The chain history is easily modeled as an append-only file. Every new block just tacks on one new header and a set of transactions and a set of receipts and that sort of stuff. We need to do a little bit more than the ETH protocol does, though, because the ETH protocol only exposes headers, blocks, receipts, but it requires clients build that canonical index themselves. And for us to have light clients that are able to expose the full Json Rpc API, we need the canonical index to be part of the chain, part of the network. This is really just piping that entire key value store into the network. It's easy to do all of this in a way that's anchored to the header chain and that's provable and resistant to people piping in junk data. But the real change that needs to happen here is the individual node responsibilities that each node on the network has. In the ETH protocol, every node on the network is required to have the full history. This is how you can just connect to any node in the ETH protocol and just start asking them for any single piece of historical data. It's kind of ridiculous that that's the expectation, but it's just the status quo. We have to break this assumption. We need a network that allows us to divide the data up evenly across all of the nodes in the network, and then that allows us to discover which nodes have the data we want. It turns out that Kademlia DHTs kind of have this as a built-in property. It is highly likely that the solution for this is going to be a Kademlia DHT. The specifics are totally up for grabs. There's a research, essentially like a proof of concept that I and my team built out over the last months called Alexandria, which takes a stab at this problem. This one is a very tractable problem to solve. And once it's solved, it's very likely that all of the Ethereum clients end up starting to get on board. We'll talk about that in a minute. And the third piece is state. These light clients need on-demand access to any part of the state. Like we said, there's things where you want to read contract data, things where you want to estimate gas for transactions, and that involves EVM execution, which involves reading contract state and accessing accounts and their code and balances. But just like the history network, we absolutely have to design this network in a way that is conducive to nodes being able to show up with a small amount of storage, offer it up for the network, and do their small part, rather than requiring every node have a very high burden of responsibility. One of the central themes here that you may see is that what we're looking at is how can we design networks that allow for clients to show up with small amounts that they can contribute to the network, and for those contributions to be meaningful. You can't do that on the Dev P2P, ETH protocol, and the LES protocol, and part of that is just a byproduct of the design of those protocols themselves. So this is something that has to be designed into the core of the protocol. So if we build these things out, this is maybe what it looks like. And this might look a little bit silly because we're essentially building out 3 new networks to support light clients. And the whole thing is completely detached from the core of the network. In reality, there's some bridging happening here where some benevolent actors or whoever are taking the data as it shows up in the ETH protocol and bridging it over into this light network. But it would be unfortunate if this was the end game, because what we effectively have is 2 completely disconnected networks, and that's not great. It means that they could lose track of each other, maybe, if an attacker shows up and starts piping data in or something like that. We don't want that to be the end state. The ideal state is for these to be a little bit more intertwined, and that's where I think that we end up once these things are built and shown to work. So every one of you who has a fully synced node on your computer has something like 200 gigabytes of space that's dedicated to chain history. It's not quite that much, but we can just call it a rounding error. It'll be 200 gigabytes at some point here. And it's very likely that many of you either have never or rarely make any Json Rpc call that touches any piece of the old parts of that data. Most of our interactions with our own nodes have to do with things like looking up our own transactions or checking recent blocks or things like that. But digging deep into the chain history isn't something that happens in a lot of the typical use cases that people have. So if there's a network out there that light clients are using that lets you fetch any piece of the history on demand whenever you want, and the cost of entry is to give it 100 megabytes of your disk so that you can host some of that data for the rest of the network as well, it's very, very likely that the authors of the client software out there are going to take advantage of this, and they're going to offer you a flag that you can use with your client that has it purge all of this old data, and then when you need some of it, it fetches it from this history network. Similarly with the state, I talked about Beamsync earlier. This was this prototype that my team made, where what the client does is it jumps straight to the front of the chain, and it just starts executing blocks as if it had all of the state in its database. And every time it hits the database, looking for an account, a piece of contract storage, whatever, and it finds that it's not there, it just goes and looks it up on demand from the network. This allows you to process blocks at the front of the chain while you do all the other work in the background, while you use something like the new Snap protocol that the Geth team is developing that is excellent for syncing all of the historical state, while you fetch all of the history from some other network. But you just follow along with the front of the chain as if you had all of the state, and you fetch it on demand when you find that you don't. The UX for this type of client is really nice. It just works immediately. You see progress right away. They actually act as sort of like BitTorrent swarms, because all of the clients that are doing something like this are all swarming on the same pieces of data, because they're all swarming on the state that's being touched in blocks that are happening. So if the state network exists, it's highly likely that client developers who want to expose this superior UX to their users end up attaching to it as well to use it. They still stay connected to the ETH dev P2P protocol. It probably needs to evolve some, because if they start ditching the chain history, then that protocol is going to have to change in ways to support that, because otherwise some of the assumptions that it makes are going to fall apart. I do not have a good, compelling story for why they switch over to our gossip network, but it's entirely possible that if they switch over to the other two, then we can just go ahead and get them onto the third one and erase that line to the core ETH protocol itself. But maybe the key takeaway here is that we need that ETH protocol to be stable. And we need room to experiment to build out these networks for light clients. And so it makes sense for us to build them independent in the beginning, and then to bring them together once we know that they work and how well they work and what the security profile is. Because we can't just go making whatever changes we want to the ETH protocol. We need it to keep supporting the core of the network. So back to this slide, I want us to have these clients. I've been staring at this problem for a long time. It's very much in line, similar with stateless Ethereum and what I want to happen there. We know that we can make clients that don't need to sync. We know that we can design networks that scale. We've looked at Json Rpc and the underlying data, and we know what these networks need to do. And we have good leads on how to do them at the network level. And across the board, we've eliminated all of the pieces that cause Ethereum clients to be such resource hogs, and why it makes it so hard to run them on low resource devices. And once you eliminate that, all that you have left is the small amount of overhead for verifying the data that you request on demand as it shows up, and the just base load of passing messages around the network. Yeah, so stateless Ethereum, there's a lot of crossover here in terms of what we're talking about. Stateless Ethereum is aimed at the core protocol. It's aimed at adjusting the core protocol in such a way that individual full clients do not have to keep a full copy of the state. The idea is we create witnesses for blocks, and we pass them around with the blocks themselves. And so a full client can receive the block and the witness has all of the data that the client needs to execute the block. This is the functionality that, it's not that we need it for the ETH2 merge, but it makes the ETH2 merge just world smoother. ETH2 builds is built on sort of an assumption of statelessness, and that is not what the core Ethereum protocol has. And so the Stateless Ethereum research efforts, which has been going on for a little bit more than a year now, something like that, is focused on bringing this concept of statelessness to the core protocol. The thing is, it doesn't actually give you when you take away all of that state data and you take away the chain history, potentially, then it doesn't actually give you a client that's all that useful, because it still can't, because it no longer has the data that it needs to serve the Json Rpc API and things like that. And it turns out that's a lot of how people use clients. We've got sort of two different, I guess, faces of the same coin. One of them is the external API that clients expose, and the other is sort of the internal API that they expose back to the network. Stateless Ethereum is about that API exposed back towards the network. It's not really focused externally. And so we need both of these things if we're going to have really amazing, awesome stateless clients. Questions?
I have one. My question is about security of this light client, how it can be sure that the data it reads correspond to the canonical data of the chain.
That is a fantastic question.
Yeah.
Was there a continuation there?
Yeah. Just because to be sure about that, it have to verify hash. It has to execute the blocks coming from the network, which is source consuming.
Mm-hmm. So the assertion that it has to execute blocks is one that I will push back on. It is likely that if a client for if this type of client is built out, that will be something that is either opt-in or something that you can opt out on, and that's going to be a decision that client developers make. But the way that Geth nodes sync today skips over 11 million blocks worth of execution. It pulls the state directly for the latest state of the chain. It trusts that it was executed correctly for the last 11 million blocks, and then it goes upon executing itself and verifying. You're right, EVM execution is expensive. And there are probably a number of nuanced attacks that could be done by a miner who mines a block with a correct proof of work seal, but with an incorrect state root. This would generally get rejected by the rest of the network, but maybe there's an attack that they can use against this type of light client. But it's going to be a very special case thing. And it's going to be very difficult to do that at any kind of scale, because it turns out mining blocks is, well, mining a bad block is costing you money, right? Intentionally mining that block today costs you like $2,500. And so the attack has to be worth more than that. So my assertion is that block execution is not actually required, but verifiable data is absolutely required. And there is no piece of this which is trusting data from the network. One of the changes that we need to make to the core protocol is to get a header accumulator added in. This is essentially a way for clients to be able to forget about the long history of headers, and then to be handed a header from deep in the history, and to know, along with a proof against this accumulator thing, and that a proof, if you have the accumulator from the front of the chain, can tell you definitively that the block you were given is part of the canonical chain and not an uncle. So that mechanism gives us the ability to only follow the tip of the header chain while still being able to be handed historical headers along with a proof and know that they're canonical. All of the rest of the data is anchored to the header. So if you're looking up a transaction, then you're going to look up the blob of transactions, or the transaction itself is going to come with a Merkle proof against the header field for the transaction tree. The same goes for receipts. If you're fetching a receipt from the network, It's going to come alongside with a proof that guarantees its inclusion under that header. So if you want to get a receipt, you're going to go get the receipt. It's going to come with a proof. You're going to need to go get the header. It's going to come with a proof. You're going to verify the proof against the accumulator, and then you're going to work your way back down verifying those other proofs. And that gets you completely verifiable data. This is what Ethereum clients do today. When a client is syncing the history of the chain, they do this all the way through for the most part. Another client sends you the block body, and it has this list of receipts and these list of uncles, and you go ahead and recompute the state root for those things and check that it matches the header, because you're not sure that they didn't just hand you garbage, or that they didn't just hand you something malicious that kind of tries to trick you. So every piece of data is always anchored back to the header chain and always provable when you can anchor yourself back to the header chain.
Did I get it right that the accumulator will accumulate the ETH hash or something like that? So you just can like read one piece of data and say that the chain behind this, the chain that's supported by this piece of proof, is all canonical, or is it kind of that?
Essentially, which are so this is pulled directly from the ETH2 beacon chain. So the beacon chain solved this problem that hasn't been addressed in the core like mainnet Ethereum protocol. The accumulator is it's a doubly nested Merkle tree, and so you essentially chunk up the history into epochs, and you build up this list of this Merkle tree of essentially like block hashes and maybe total difficulty, because that's another piece that's like not easy to prove when you only have a piece of the chain. And then every time you fill one of those up, every time you finish an epoch, you just grab the Merkle root of that Merkle tree and you stick it in the master accumulator. So the master accumulator grows very slowly. It only grows one entry per epoch. And so the master accumulator grows very slowly. It's something that clients can easily keep track of and keep in memory. And then the proofs are against the master accumulator and the the Merkle tree that's dangling off under it for whatever epoch we're talking about. So yes, if you have the accumulator, then people can give you proofs and headers that, when verified, guarantee that the thing that they gave you is part of the canonical chain at whatever position it's supposed to be in.
Oh yeah, I get it. Great.
Cool.
And you will also have to attach this kind of proof to each piece of state you read, right? To be sure that you read the state from the canonical.
So the state is probably just anchored to the state root itself. And then it's up to the client itself to then verify the state root is indeed part of a header that they care about. So if they're trying to, read state from a specific state root, they already should have verified that the header that they're looking at is genuine, at which point they take the state root and then walk into the state network to start accessing that data. And yes, that data either comes back with Merkle proofs or is kind of inherently provable based on how the network's designed. And the state network is the hardest problem that we have to solve here. It's the nastiest piece of data that Ethereum clients work with. It's huge, it's effectively random access, it's complicated, and the proofs are heavy. So so the state network is the hardest problem to solve among the things that have to be done here.
Yeah, thank you for clarification. Yes, the state is definitely hard part.
I just had a question about security of data, making sure that what happens when data is lost. Is that similar to stateless, where if you care about a bit of state, you should keep it on your disk, and therefore you can set up a proof whenever you need. And if you have lost it, bad luck to you. The same with, I guess, history. If you've got a balance in an Ethereum account, you need to personally keep the history of every transaction so that you can prove that, because statistically the rest of the network, it could potentially get lost if everyone's only storing partial.
Right. It's a pretty standard concern, and you're not wrong to like it's definitely something that has to be taken into account. There's a couple of different sides to this problem. So one of them is that this isn't the core network. And so there's one argument to be said that it's okay if these networks lose information every once in a while. Totally not ideal, totally not something that we want, but in the event that these networks lose information, it's easy to patch back up. That's one of the nice pieces, is that we can always reach back into the core ETH protocol. We can always go find one of the fully
okay. So assuming, so what one approach is to always keep a core network that does have
so
every node having all the state. Right?
Yep. Okay. One approach is to never throw away the assumptions that the ETH protocol makes, and to just still have our pile of full nodes that all have all of it. At which point a handful of benevolent actors can easily patch up missing state. The other way to look at this is, if we have, let's say that we're modeling this as a DHT, and we've got 100,000 nodes, and each of those nodes shows up to the table with 100 megabytes of storage. If I'm not horrible at math, then what we just got out of that is something like 10 terabytes of combined storage across all of those nodes. If we're talking about the chain history, which comes in somewhere in the 100 to 200 gigabyte range, call it 200 gigabytes, then if you just take all of the chain history, spread it out evenly among all of those nodes until they all fill up all of their offered 100 megabytes of space, then you end up with a replication value of something like 40 or 50, might be higher, and that's pretty good. The thing is that chances are the more popular stuff is going to be replicated more thoroughly, and the really, really old stuff is probably not replicated as much. But like I said, it's relatively easy to patch up missing data. So my prediction is that in the very beginning, when these networks are small, they will lose data. They will house only the most popular data, and they will operate at capacity. The trick is going to be bootstrapping the networks sufficiently large enough so that they're still useful in that model. They may not be able, like the state network, in one of the models that we're looking at, we'd really like to make it an archive node. It would be really great if we can make the state network not just the latest state, but every single snapshot of historical state that's ever existed. That would be really, really nice to have at a network level, because it turns out running an archive node is even more prohibitively expensive. You're talking about needing 6 terabytes of high performance disk just to run a Geth archive node. TurboGeth has done some awesome stuff. It's still 800 gigabytes of hard drive space to run a TurboGeth node. So archive nodes are expensive and few and far between. If we can build out the state network so that it's an archive node, that's amazing. In the beginning, we probably don't have the capacity. But as these things grow and gain more usership, it is totally non-trivial for the network sizes to get large enough that losing state just may not happen. And if the networks are sufficiently big and offer sufficient storage capacity, then the data doesn't get lost. It's that ugly middle zone where we're not quite big enough to house all of it yet, where we need to be, focusing on patching up missing data.
But similar to stateless data, you can make that the responsibility of the people who care about that data.
Absolutely.
So, for example, if I've got a balance and I know it's made up of these transactions, I might direct my node to store them.
Mm-hmm. I think the even like more compelling use case there is that the Ethereum Foundation, that's not actually their name, whatever their actual name is, the company that Nick Johnson's doing that does ENS, it's in their best interest to run some infrastructure that monitors this network for all of the state in the ENS contract. And when it finds some of it is missing, that it patches it up. Same
Yeah,
goes for Maker. Same goes
exactly,
for
exactly what
Uniswap.
I'm thinking. It means no individual actor stores the whole state, but they're going to make sure that there's at least one copy of the state portion that they care about, which is going to be very small. And if they ever, I finish with the contract, I never need to use it again.
Right.
The balance of my accounts is zero. I'll just forget it and turn my node off.
Exactly.
And if other people forget it, who cares?
Mm-hmm, mm-hmm. So the nice thing is that in all of the designs we're looking at for both history and state, it is relatively trivial for a very small handful of benevolent actors to keep the network completely healthy in terms of the data that it houses. And that is a really nice property to have.
I have another question. So at the beginning, when you started talking about the three networks, you mentioned them as being an alternative, like the existing network would still be there because it needs to be bulletproof, and the new three networks might not need to be. But if you reach the point in which those three networks, is the idea that eventually we might really use those three networks and forget about the other one?
This is my ideal end state right here, is that we build out the three networks. And then, like right now, like most full clients, they all look about the same. There's not like a very big spectrum of choices available to you as a client developer. You have to do a bunch of things, and they all end up looking roughly the same. My hope is that building out these different networks sort of stretches the clients out across this spectrum of full, heavy, big, beefy, storing all of it, all the way to the far other end of utterly lightweight, doesn't even execute blocks, just verifies the data that's coming in over gossip and verifies the data that it fetches on demand. And there's a whole canvas there in the middle that other clients can land in, whether or not that's by feature flags or whatever, and they can do that by leveraging the functionality that we want to build out in these different networks. So I think the answer is, if I remember the question specifically, that the answer here is that the ETH protocol very likely stays around, maybe indefinitely. What it looks like and how it changes is unclear, but it's likely that clients start also participating in these other networks in order to get access to the functionality that they expose, so that they can expose these nice features to their users, freeing up 150 gigs of hard drive space by not storing all the history, making the client usable immediately by reading state out of the state network to do Beamsync or something similar.
So would it be necessary to turn those three networks into to make them, let's say, bulletproof, or will we always rely? Yeah.
When you say bulletproof, the guarantees that we have about network security are always a little bit fuzzy, right? There's like certain kinds of I don't know. The word bulletproof kind of like struck a nerve there, I guess. The needs of light clients and the security demands that the use cases that we're targeting need are just much, much lower than that of a full node operator or even a miner, right? Like miners need this certain level of just like bulletproof, guaranteed access to the network that can't be DOSed, that like, right, if there's certain types of vulnerabilities in the core ETH protocol, then the whole protocol grinds to a halt. And that is a catastrophic like failure. That's a failure mode that like we're utterly, we cannot have. But the same is not true when we're talking about light clients. If light clients suddenly can't access the chain, it's still really unfortunate, but the network just carries on without them. I'm not saying that it's not significant. It would absolutely be significant if one of these networks is attackable in a way that all of a sudden the 10,000 light clients that are using it for wallet access can't transact with the network. That sucks. That's like not a situation we want to find ourselves in. But it isn't like market crashing, like doomsday level failure, which it would be if we're talking about the core network. So I can't say specifically what it is, what that's going to look like, but it is absolutely part of the design process, is looking very closely at and understanding the security profile of each of these things. Cool. I think I have a couple of slides left. Let's see what happens next. Oh, I have no slides left. Cool. Are there any more questions before we do this this other part where we advertise what's coming next?
I have a quick question back to your diagram there. Is it kind of like accurate enough to think of stateless clients as being in the same bucket here as the light clients?
Similarly, yes. I really have wanted to build out a graph of all of the sort of like different types of client functionality that are possible, because I have it in my head and it's fascinating and it fuels all of this research. And it isn't even a like one-dimensional spectrum with like full on one end and stateless or light on the other. Maybe the difference between a stateless client and the light client that I'm talking about is that a stateless client definitely is executing blocks. That's kind of like one of the presumptions, that when at least I say stateless client, I mean a client that does full block verification. And I've recently realized that because EVM execution is heavy, that we have to build with a design that on the very far end of the spectrum, we don't even need to execute blocks. And so that's why I've sort of like shoveled that off the requirement list. But if you step back over a little bit closer towards the full end of the spectrum, then you absolutely reintroduce block execution, because that is one extra layer of security that you can build into your client. But when we talk about stateless clients in the context of stateless Ethereum, it really isn't focused on the external interface that clients are exposing. In fact, one of my frustrations with the stateless roadmap has been that if we accomplish the stateless roadmap, we've done some really awesome stuff. And the core Ethereum protocol is in a much, it's easier to merge it into the ETH2 ecosystem that has this presumption of statelessness. But you can't build a very full-featured client. Like just because the client is stateless doesn't mean you can still expose the full API. A stateless client might be a very excellent like piece of infrastructure to have on the network itself, but unless you build out this other functionality, you can't, like the Json Rpc API doesn't exist because you can't serve the data just from the ETH protocol. So we have to do both sides of this. We have to do the thing that's inside the protocol that makes stateless block execution possible. And we have to do this thing that's really more focused on the user layer and on the external APIs to facilitate actually serving the Json Rpc API, even though you don't have all of the history.
Thanks. Yeah, very helpful.
Yeah, I'm going to say that again, actually, because I think it's probably something that gets missed. The stateless Ethereum roadmap is focused on delivering clients that do stateless block execution. And the reason for that is that we want to let clients forget about the state. But if all that we do is that, then your client can no longer serve ETH call, ETH estimate gas, ETH get balance. These are very necessary endpoints for almost any application you're going to build on top of a client. And so we have to do both sides of this if we're going to have stateless clients also be highly useful.
Absolutely, Piper. I think you're spot on. I think you've got to be able to do ETH call and you could get balance, even if it was just for a narrow set of contracts that you're interested in or addresses. Yeah. So look, thank you for such an amazing talk. That was absolutely awesome. And we'll all give you a virtual round of applause. So thank you. Yes. Yeah.
So I've got your slide. I've got your slide up here.
Yeah.
You want to give the?
I'll I'll talk to it. So, in 2 weeks' time, I'm going to talk about. It's actually called GPACT now. So it's a general purpose atomic cross-chain transaction technology. So it's a layer 2 technology that allows you to do function calls across blockchain and atomic. So you're sure that when you do have a function call on one blockchain to another blockchain to another, you can be sure that either the whole call graph is committed or it's all discarded. So I'm going to talk about that protocol. And then potentially the day after that, there's not written here, but there's going to be a talk co-hosted by this meetup and another one over in California, which is going to be about zero knowledge proofs and business applications of zero knowledge proofs. Then on the 17th, could be the 16th, depending on your time zone, Matt is going to talk about the EIPs that are likely to land in 2021. And then 2 weeks after that again, Mikhail is going to tell us all about the ETH1, ETH2 merge. And this is actually the old title. So he's done just like Piper and changed his title around. But it is more than just whether the merge should happen before sharding or after sharding and the advantages and disadvantages. There's a lot more to it. But the ETH1, ETH2 merge, I think, another really exciting talk. And I believe we've even got another talk after that scheduled, but I can't even remember what it is. But we also have, yes, the workshop. Yes, there's the cross-chain workshop. And so that is, I've been on a whole heap of Zoom calls, as I'm sure everyone's been, and I find that after 2 hours, I just zone out. And so this is a mini conference, and it's over 4 sessions of 2 hours, which is across 2 weeks. And so the idea is that we're more likely to have people actually engage, and so you'll turn up, maybe you speak, and you'll listen and you'll discuss. And in fact, for each of the talks, they're only going to be 15 minutes long, but then there'll be 15 minutes question time. So it is going to be a research-based workshop based on cross-blockchain communications. I've engaged with researchers all around the world to put in proposals. So you don't have to write a new paper. It's a matter of you've got something on ETH research, or you've published in a conference, or it's on archive.org, or you've got a YouTube video or whatever. And so we're going to put that up. People can review that before the conference And then it's really going to be about discussing what are the benefits and disadvantages of each of the technologies. So the call for speakers is still open for that. So go to the website, you'll be able to, or be redirected to EasyChair. If you go to the website, you'll also be able to register via Eventbrite. Registration is completely free. So hope to have lots of people along. And that is definitely the last slide now. So look, thank you again, Piper. That was an absolutely awesome talk. And yeah, thank you.
If anybody wants to join in on this effort, which will be ongoing for a while, there are channels in the ETH R&D Discord. ETH R&D Discord is a fantastic place for really high-level, high-quality technical discussions of the protocol. We're all in there. Come ask us questions. Come be part of it.
Sounds awesome. All right. See you later, everyone. Have a great day.
Awesome. Thanks, Piper.
Thanks, Piper.
Piper.
Thanks, everyone.
Thank you.
Thank you. Thanks.
See you, Sandra.